we found potential energy initially by looking at the work done by an interaction force within the system. So we wonder, can we reverse this procedure? Can we find the given the system's potential energy, can we find the interaction force? So let's imagine that we have the object undergoing a very small displacement delta S. The reason why we're thinking very small displacement means that the force that this object would be feeling would be constant, essentially constant, over a very small interval, even if it's not constant over a greater interval. And in this case, if we're looking at the overall potential energy of the object, that potential energy of the object is probably coming from many different forces that are all acting on this object. And so what we'd be finding here would be, for example, the average force that the object would be feeling based on all the other forces that are acting on it at a given moment. Now, we defined our potential energy as the negative of the work done by internal forces. And so when those internal forces do negative work, when they take that energy away from our object, that object retains potential energy instead of that energy just disappearing. But work is force times displacement if it is a constant force. And again, we're assuming such a small displacement that we can assume force to be constant over that small interval. Then we can rewrite from this equation, combining these parts, that the force felt by the object would be the negative of the change in potential energy per change in position. When we consider this small change in position, not just a very small change in position, but in fact an infinitesimal change in position, this change in the potential energy becomes the derivative of the potential energy. And thus, we can see from this equation that we've just derived that the force on the object is the negative of the derivative of potential energy with respect to position. So the force on the object is the negative of the derivative of potential energy with respect to position. What that means from a potential energy graph, like we've seen before, where we're plotting energy versus position, is that we look at the slope of the tangent line, that's our derivative. In this case, we have a positive slope, and that tells us that the force will be in the negative direction of our dimension. And so that means that in a potential energy situation like this, we'll feel a force to the left, which will make us tend to move to the left. It will make us tend to reduce our potential energy and convert that potential energy into kinetic energy. We see here another example. Here we have the energy diagram for a spring. We are saying that the equilibrium length of the spring is set to be 0, and so you have potential energy of that spring, which is parabolic in nature. When we're looking at the force that the spring would give you because of this potential energy, we see that over here we have a positive slope, and so we would have a negative value of the force. As you move farther up, the slope is greater, and so you would have a larger negative force for a bigger value of x. When you're closer in, the slope is less, and so you'd have a smaller but still negative force for a smaller value of x. When you look on the other side, you have a small positive force there, a small negative slope here, which would give you a small positive force. As you move your way out, you have a little bit larger negative slope, so you have a larger positive force. And as you move farther out, the slope gets larger negative, so you have a larger positive force because of that relationship that we derived to say that the force would be the negative derivative of position with respect to x in this case, if we're talking about our x coordinate. So looking at the potential energy graph of a spring, we found the force, and we've basically recreated the force for a spring. We've recreated Hooke's law. And so we see that the value of the force is equal to the negative of the slope of the tangent line of the potential energy versus position graph. This behavior holds for simpler or more general potential energy graphs as well, that the force is the negative derivative of the potential energy curve. If we have some general potential energy plotted versus horizontal position, we can look at the behavior of that curve and see how what the force would be in each case. In this segment, the slope is negative. It's a downward slope, so we'd have a negative derivative. A negative would give us a positive force. That means that in this case, our force would be to the right. It would try to be pulling us to the right so that we would decrease our potential energy and increase our kinetic energy. When we have a horizontal segment, the derivative of a horizontal line, the slope of a horizontal line is 0, and so we'd have 0 force. In this area, there's no change in potential energy with our position, so there's no preference to be at one location compared to another location, so there's no force there pushing us one way or the other. Finally, when you have a positive slope, you have a positive derivative here, and so the force would be a negative value. And so in that situation, your force would be pulling you back in. The idea here is that as you're moving to the right, you're increasing your potential energy the whole way. That means the force that's causing that potential is taking away kinetic energy, slowing you down, so that you're giving up that energy and turning it into gravitational potential energy.